Today we are starting Chapter 9, Combinatorics. Things we're going to look at through this chapter are things like the addition and multiplication principles, solving problems involving permutations and combinations, establishing using identities that are associated with Pascal's triangle, solving problems using the pigeonhole principle, and finally understanding and applying the inclusion-exclusion principle. So just to demonstrate what are combinatorics, or an element of it, and how is it used in the real world, here is a fact for you. Pretty much every time you shuffle a deck of cards, you create a combination that has most likely never been created before. So what we mean by that is that the way that the cards are arranged, the order of them, has very likely never been arranged in that way from any other shuffle that's ever been created. There are quite a few cards, 52, but to claim that nobody has arranged it in that way before is a pretty interesting claim. So what we're going to do is we're going to look at the mathematics behind this in this chapter. You can actually probably figure it out after today's lesson as to why that is the case. But these are the kinds of things that we're going to look at through this chapter. So what are we starting off with today? 9a and 9b. 9a is all about counting methods and 9b is all about permutations. What you need to be able to do is utilize the addition and multiplication rule to find the number of ways that we can do something. Understand the concept of permutation, understand factorial notation and how it is used in permutations, and finally solve permutation problems with and without restrictions. So before we go through any instruction, I'm just going to give you this question. Give it a go. We're going to travel from Melbourne to Sydney. Well, not us. Kara's going to do that. And she has a choice between 3 different flights and 2 different trains. How many choices does she have? This might seem super obvious to you, and it really is. It is that simple. She can either choose 3 flights or 2 different trains. That's it. So she has 5 choices. Whilst this might seem very basic, this is the basis to this entire chapter. We're trying to think about how many different ways we can do something. So in this case, she has 5 different choices because she has a choice of either the flights or the trains. This we call the addition rule. So in general, to choose between alternatives, simply add up the available number for each alternative. So if I have m number of ways of doing something, n different ways of doing another task, the key here is that I can't perform both of the tasks. So in Kara's case, she can't catch both a flight and, what was the other one? A train. So she can't catch both a flight and a train. She has to choose one or the other. Then there are m plus n ways to perform this rule. And the word that can really help you out with this is the word or. She can either do this or this, and that is what we usually associate with adding. So let's practice that a little bit more. We're at the library this time, and Alan is having trouble deciding which book to borrow. He has a choice of 3 mystery novels. He's got 3 biographies or 2 science fiction books. How many choices of books does he have? Well, the same idea. He can either choose 3 mystery novels, 3 biographies, or 2 science fiction books. So in total, he has 8 different choices of what he can take. So what happens if we don't have to just choose one or the other? What if we can choose things but complete them one task after the other? Well, you have been exposed to tree diagrams before, and that's a really good way of being able to explain how we can perform tasks or do tasks in a sequential order. So if you have, tossing the coin, for example, and you can toss it twice, well, you've got something that you can do the first time, and then you've got options of what can happen the second time. So the ways to figure out in how many ways we can arrange things or how many choices that I have in total is by utilizing a tree diagram. So you can see here, I've got my first stage where I've listed out all my possible options, and then I've got my second stage where I can list out the possible options in the second phase as well. Now, we're not really looking at probability at the moment, so the probabilities are not important, but what is important are the options. So if I go down this route and this route, then my 2 choices are head. Whereas if I go down this route and this route, then my choice is head and tail. Let's have a look at this through an example. So we've got a restaurant that has a fixed menu, and it offers either the choice of fish or beef for the main meal, and then we either get to choose cake, pudding, or ice cream. So you can see how there are 2 stages here. I either choose fish or beef, and then I choose either cake, pudding, or ice cream. So those are the 2 stages that we will draw into our tree diagram. So at first, I can choose either the fish or the beef. And after that, if I choose fish, then I've got the choice of cake, pudding, or ice cream. And then same thing here. I can choose either the cake, pudding, or ice cream. And I can see that here I've got my first choice, which would be fish cake, fish pudding, fish ice cream, and so on. So in total, I actually have 6 choices. Now, how else can we get to this number 6? You might be able to see it. In the first phase, I had 2 different choices, and then in the second phase, I had 3 different choices. So in total, I will have 6 choices of meals in this specific case. This is what we call the multiplication rule. So the idea is that we have successive stages. We have one choice after the next. If I have n ways of performing one task, n ways of performing another, and I can do one task after the next, then I will have m times n ways of performing both tasks. So the key word here is and, because I'll be performing both tasks. Let's apply this to another example. When traveling from home to school, James either takes a bus or walks. So that's our first stage here. He can either take a bus or walk. And then he can either catch a tram, train, or another bus. So that's the second stage. Of course, we can draw a tree diagram, but we can also use the multiplication rule. So we have 2 choices in our first stage, and then we have 3 choices. So we can see that in total, James will have 6 choices to being able to travel from home to school. Example 5, how many paths are there from point P to point R, traveling from left to right? And we did just complete this in our last chapter where we looked at networks and we had to think about all of the different paths and routes that we can take. Well, now we can utilize the multiplication rule, because in my first stage, I can see that I've got 4 choices, and in my second stage, I've got 3 choices. So what can I do? I can multiply those to give me 12 different paths, 12 choices that I can make. Now, there are some harder problems where it's not either the multiplication or the addition rule, but you need to kind of use both. So in this case, we're trying to travel from point A to point E, and we want to figure out how many different ways that we can do this. So we can see that even though I have lots of different options here, and they're one stage after the next, I can see that if I choose to go this way, I can't also go that way. So what that leads me to think of is that idea of or. I can either choose to go the upper path or the lower path. So when I have this or, what I can recognize is that I need to figure out how many options do I have at the top, and then how many options do I have at the bottom, and I have to choose either this one or this one. And when I have that or involved, I will be adding my 2 different options. I can see because there are many sequential stages, I will use the multiplication rule at the top and multiplication rule at the bottom, and then I will add my options up. So let's consider them. I'm going to first choose my upper path. So from A to B, I've got 2 choices. B to C, I've got 2. C to D, I've got 2. And D to E, I've got 1. So in total, I've got 8 different paths that I can take. And then if I consider my lower paths, I've got A to F is 1, F to G is 3, G to H is 3, and then H to E is 1. So in total, I've got 9 paths. Now I need to make the choice of whether I want to go from the top or the bottom. So I'm going to add these up, and it's going to come to 17 paths in total. Okay, and finally, this is an example of where these problems might get even more difficult. It's not just as straight as using the multiplication or the addition rule, because as we're going to read in a sec, this one changes the condition each time that one of the stages is taken. So we've got a bag that contains 1 blue token, 2 red tokens, 1 green token. 3 tokens are removed from the bag and placed in a row. Now at face value, it seems like there are 3 stages, right? I'm going to select 1, 2, 3. But what happens in each stage is that 1 token is actually removed. So the number of choices that I have is going to change. And really the only way to be able to figure this one out at this stage is through a tree diagram. So the addition rule is not going to help us out because we don't know which stage comes first and what's being taken out at each item. So let's consider the first stage. I can either choose a blue, a red, or a green. If I choose a blue, then I don't have any more blues left. So that means I've only got either reds or green. And you don't have to write these, but just to try and help you out, because now I'm trying to think of, how many tokens are left and I might get confused, I might just quickly write next to it how many there are, just so I can keep that in mind. So in this case, I had 1. Here I've got two for the red and 1 for the green. So when I've removed the blue, then I don't have any more. And then I've got 2 reds and 1 green at this stage. The second one, if I remove a red token, well, I'll still have my 1 blue token left. I will only have 1 more red token left, and then I've also got 1 green token. And then the same thing with the green, because I only had 1 green token, which means I've either got a blue or red left. So blue is 1, and red is 2. Now we're going to do it again. It's going to get a little bit messy, I think, but if I choose a red token here, then I still have one more red token, and I also still have one more green token. And because I don't need to consider another phase, I don't need to write the numbers in this case. If I choose a green token then, though, I don't have either the blue or the green anymore. I've only got one red token, so that's my only choice in this case. Now, if I consider the red over here, I've chosen a red, so that means and then next I choose a blue. Well, I don't have any more blues left. I do still have one more red though, and I will have one more green. If I choose the red token though, that's all my red tokens gone, but I will still have a blue and a green left. And similarly to the first one, if I go down the green path, then I've removed a red token, but I still have one left. I've removed the green token, so I only have blue left. Finally, let's consider the green. So if I remove the green and the blue, well, the only thing that I have left is red. And I do have 2 red tokens, but it's still just a red. And if I go down the green, then red tokens, well, I still have one more red token, and I also have a blue token. So you can see in this example, it is a little bit more complicated, and you do need to sort of be on your toes in terms of what is left. And that's why it's not as simple as using the addition or the multiplication rules in this case. Now what we can do is count the number of options we have. So every branch on our third phase is going to count as one particular option. So that's 1, probably won't circle it, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we can see that there are 12 possible arrangements. So 12 different ways in which I can pull out these tokens. This one definitely requires a little bit more thinking and a little bit of patience as you're drawing your tree diagram. That's it for next exercise 9a. So what we've been able to achieve so far is utilizing the addition or multiplication rule to find the number of ways to do something. And we're now going to look at permutations, which will cover these 3 dot points here. So what is a permutation? A permutation is basically the ways that we can arrange objects. And I know we've already kind of spoken about it, but we're going to define it a little bit more in this exercise. Permutations are concerned with arranging objects in a particular order. So I care about the order that they are in. So for example, how many ways are there of arranging 3 different books on a shelf? I'd suggest pause the video for a sec and see if you can figure it out yourself. Well, one way we can think about it is to create 3 different spaces on my bookshelf like this, and to think about how many options can go into one. So if I have 3 different books, then there are 3 different things that I could place here. But if I've already placed one, then I only have 2 books left. So in my second phase, I'll only have 2 options. And if I've placed a second book in there, then in my last phase, I'll only have 1 option. Now, thinking about our multiplication rule previously for the successive stages, so I'm going to choose a book and then another one and then another one. All we need to do is multiply each of these options, which is going to give me the total number of choices, which are 6. And if you try to list out 3 different colors or 3 different books and try to figure out the different options that you have in arranging them, you'll find that you've got 6. This method, which is termed the box method, is one of the simplest ways to being able to figure out the ways of being able to arrange different things. So one thing that hopefully you've recognized is that each time, because I've chosen an option, I then have 1 less option the time after. So we're going to define this using this particular rule, and mathematicians have gone ahead and said, all right, it's time to term this as something, and that something is what we call a factorial. So in general, if n objects are arranged in a row and there are n choices for the first position, you'll notice, as we just had before, there's going to be 1 less choice for the next position because I've already placed 1. Then the next one, I'll have 2 less choices than the original one because I've already placed 2 items. And you keep going until there is only 1 choice left. So in general, this is what this formula will look like: n times n minus 1, n minus 2, and so on, all the way till we hit 1. This particular operation is what we call a factorial, and we denote it using an exclamation mark. So if we have n factorial, then it's equal to n times n minus 1, and so on. So for example, if I had 4 factorial, then that would be 4 times 3 times 2 times 1. So now let's apply this concept to example 9. We've got 12 students and they're going to have their photos taken. How many ways are there of arranging the group if they all sit in a row? So of course I can do the box method and think about, okay, there's 12 options at first, then one student has sat. Then there will be 11 students, then the next person sits, then 10, and so on, all the way till we hit 1. This can be summarized as 12 factorial. And at this point, because the number is going to be pretty large, we do want to use our CAS calculator. So at this point, pull out your CAS calculators and see if you can find that factorial button, which will be right under the enter button. There's a question mark and an exclamation mark. Now, my CAS on my iPad looks a little bit different to yours, so I'm not going to be able to find it in the same position, but it's under the enter button. So this is what my CAS looks like. I'm going to go ahead and type in 12, and I'll find my exclamation button, which should be just the normal keyboard. When I press enter, you'll see you have a lot of numbers, a very large number there. So if that's 12 factorial, imagine shuffling a deck of cards, which is 52 factorial, so you can see how large that number is going to be. Okay, so if I work that out, that's going to be 479001600. Example 10, how many 4-digit numbers can be formed using the digits 1, 2, 3, 4 if they cannot be repeated and if they can be repeated? So if they can't be repeated, just as always, we have 4 options for the first one, 3 options for the second, 2 options for the first, and 1 option for the last, which we can summarize as 4 factorial. We can either complete that by hand or we can complete it on the CAS calculator, which will equal 24. Now, what happens if they can be repeated? Well, this is a little bit more interesting because if we try out our box method, you can either write the boxes or just freeform, whatever you prefer. Think about it like this. I have 4 options, 4 different numbers that I can place in the first one, but because I can repeat, then I still have 4 options the time after, and the time after that, and the time after that. So when they can be repeated, it's just going to be 4 to the power of how many stages I have, because I can utilize every option in each time. And that will equal 256. So that's how many ways I can form a 4-digit number using the 4 digits 1 to 4 if they can be repeated. Now, not all arrangements require me to use every single number. So in this particular example, a painter is to paint the 5 circles of the Olympic flag. He can't remember the colors to use for any of the circles, but he knows that they should all be different. He has 8 colors of paint available. And how many ways can he paint the circles on the flag? Well, the box method, as always, my favorite thing, will really help us in figuring this out. So he has 8 colors of paint and we need 5 different colors. So I have 8 choices of color for the first one. Then I have 7 choices, then 6, then 5, then 4. So you'll see that this time, instead of going all the way to 1, it cuts off here, which is why we can't use our factorial as normal. So what we can do though is multiply each one of these because it is in a successive stage. So go ahead and type that into your calculator while I type it into mine. That will equal 6,720 different ways. Now, as I said, we can't use the factorial, but is there a way that we can get to a formula that helps us a little bit using factorials? So if we had what we just had before, so 7 times 6 times 5 times 4, what would a factorial actually look like? It looks like going all the ways from 3 to 1. But I don't want those 3 to 1. So what can I do? I can divide it by 3 to 1 so that these numbers will essentially cancel out. So what do I have at the top? I have 8 factorial, and at the bottom, I have 3 to 1, which is 3 factorial. What's the relationship between these? So how can I possibly get to 3? Well, the 8 factorial is just the number of objects that I had. And then the bottom number 3 can be taken from the number of objects I had minus the number of objects that I want. And then it will be that factorial. So 8 minus 5 factorial. So that's how we can actually get to our permutation formula. So in general, if I have n number of objects and I have r different ways of doing things, I can summarize my permutation formula to look like this. And one way that we write this is I have n number of objects permutation because I want to arrange it, and I want R number of options. And that's basically what this slide is saying. So the number of permutations of n objects taken R at a time is denoted by this particular formula. Now, of course, you can use this formula right away. I still tend to use the box method. I don't know, for me, it's so reliable, just makes a lot of sense, but absolutely you can use this if you would like. Let's go ahead and apply it to our final example for today. So for example A, using letters A, B, C, D, E without repetition, how many different two-letter arrangements are there? So we might just use the formula as practice. So I have n number of objects and I want two different arrangements. Or rather, sorry, I want two letter arrangements. So using my formula, I can say 5PR. So that's 5 and then 5 minus 2. And that's going to be 5 factorial over 3 factorial. And then we can chuck that straight into our calculator, which gives me 20 different choices. Part B, 6 runners compete in a race. How many ways can the gold, silver, and bronze medals be awarded? So again, I've got 6 different objects and I only want to choose 3, which is the gold, silver, and bronze. So we're looking at 6P3. So that'll be 6 over 6 minus 3 factorial, 6 factorial over 3 factorial, which is 120 different choices. As I said, you can absolutely do this using the box method. So for example, over here, I would say for the first example, we have 2-letter arrangements. So I have 5 options in the first, 4 options in the second. So that gives me 20 choices. And then for part B, I want 3 people to win the medal. There are 6 options for the first one, 5 options for the second, and 4 options for the third. And when you multiply those, you get 120. So whichever method you feel comfortable in. The final thing I want to tell you today is how to do this on your CAS calculator. So these are your instruction. You can go to menu, probability, permutations, and you end up with this little symbol, NPR. And then basically you put in your N value, which in this case is 7, and then you put in your R value, which is 4, and it spits out the number for you, which makes it a lot easier. You can also just go ahead and type straight away NPR. So that's a much easier way to do it. That's it for today. That's exercises 9A and 9B.